Okay, welcome to class, everybody. We're going to go through our learning objectives, but first, the most important question of the day is, would you rather see, or maybe we could say, would you rather learn about deformation mechanisms by watching Thor's hammer Mjolnir get made or Jon Snow's sword Longclaw? So get your answers in. There's no correct answer here. Well, there's a correct answer, but I will give you credit either way. Okay, so while you're getting your answers in, here's what we're going to cover today. We've talked about... Oh, sorry. I'm used to the old clickers. We didn't have to do that. Okay, so we've talked about crystal structures. We've talked about imperfections. We've talked about dislocations. But up until now, they haven't really meant anything. This chapter is going to do something with those dislocations. For example, we're going to relate them to plastic deformation, right? We're also going to talk about how dislocations interact with one another. We'll be able to do a calculation for slip in a single crystal. We'll talk about what slip is and the complex way that it happens in a single crystal. And then we'll probably talk about twinning, and that's probably all the time we've got. So, if you're just coming in, we got your choice to learn about deformation and how they relate to plastic deformation by learning about Thor's hammer or Jon Snow's sword. Okay, we're going to close the poll. Get your answers in. Okay, what do people think? People want every year. Every year. It's very disappointing. Very disappointing. All right, let's do it. Yeah, this is the closest it's been, maybe. Marvel fatigue is even reaching my students. Year after year, we're inching closer. All right, let's see it. Okay. Let me pause this till we get... Do I not have volume? Oh, wait for it. Maybe. Let's see if we have any volume. Oh, that's sad. All right, we have no volume. That makes me sad. Hold that thought. This is so much better with the volume. Hold that thought. I see the problem. I need my big 80s boombox in here. No. All right, my apologies. There's no audio. That makes me sad. That's real sad because it's full of like death metal and clanging, but you can imagine the death metal and the clanging, and it's almost as good. What we're seeing here, it's a YouTube show. If you haven't seen it, it's called Man at Arms. It's kind of rad. They make props for Hollywood, right? And a lot of what they do is all material science. They don't know it. These guys have probably never taken a material science class in their lives, but they understand the principles, and if you walk through what they're doing, it's pretty clear what's happening. So they're making the hammer that Thor uses, right, or a replica of it, right? I don't know if this is the actual one that's in the movie or not, but they're making it here. They start out with some steel. They draw basically the outline here. This is the worst without audio. He's got the handle there. It's the pommel. Hey, we can turn on the subtitles. Good call. Let's do that. There it is. All right. That's a good idea. Okay. They're doing the basic cuts first. Okay, Alicia's core line is not Alicia's core line. They're going to score a line, right? So they're scoring a line because they're going to bend this thing. Now, when you score a line, why does that help you bend a straight line? What material science is happening there? Deformation. You're definitely deforming it. Why is it the case if you've got a sheet of metal and you scrape that surface, in this case they put more than just a scrape, they sort of grind it down a little bit, that they're able to bend it right on that spot? Yeah. Yeah, so surface flaws typically have to do with fracture, right, where the crack propagates. These aren't really brittle materials, they're ductile, so that's not exactly it. So what else is going on there? Why does it help you bend it in a nice straight line when you score that surface? What do you think, Ashton?
Because the surface has, if you bend it without the scoring, the surface has farther is being pulled apart more than deeper in the material?
No, I don't think so. Any other thoughts? I don't know the right answer. I'm just guessing myself. In the back, what do you think? That's what I think, right? You're applying the same stress to the whole plate. If you're bending it, the whole thing's got some bending moment. But if you've reduced the cross-sectional area, then the local stress there is greater, and it's going to yield first. That make sense? So I think that's what's going on there. Okay? So they've scored it. Okay, they're going to bend these things so it's roughly the right shape of the hammer. To do so, first, they heat it up. Why on earth do you have to heat it up before you bend it? Or why is it a good idea to heat it up before you bend it? It's going to increase the ductility. That just means what? Two things, right? It means it won't break, but you don't want this steel to break when you bend it. Just like a frozen banana would fracture if you bent it, but a hot banana will just bend, right? Here we got the same thing, but with a sheet of metal. I don't think I've ever used the word a hot banana, but there you have it. All right. So they're bending this here, and because they scored it, they get this nice uniform bend. Okay. Okay. So they're getting it roughly hammer shaped. This is so much worse without the guitar, but all right. They're drilling the spot where the pommel's going to go through. Trust me, it gets worth it. There's a cool part coming. Okay, lots of geometry. If you thought that you never had to use geometry, you were wrong. You always have to use geometry. You learned it for something. Okay, they're drilling that out. Once they get all the different pieces drilled out, they're going to have to join them together. To do that, they have to cut away some excess material. That's what he's doing right now. If you were just to bend that together, there'd be too much overlap, so they're beveling it away so that these different pieces can come together. All right, TIG welding stands for tungsten inert gas. What on earth is tungsten doing here? What's inert gas doing here? What is this welding? What's happening with TIG welding? Any TIG welders in the audience? Any welders? Sam, how do you weld? Or what's going on here? What do they need? Anybody else welded before? What's going on here? Yeah, in the back.
You're using electricity
Yep.
to form the metal at the joint.
Close. Yeah, I think you're on the right track. You take a tip, which is metal, connected to a big electrical generator, and that generator needs to be able to provide a large current, right? So we need to be able to send a lot of electricity through it, and a pretty high voltage because you want it to arc, right? If there's a small difference in voltage, like a 9-volt battery, it's tough to make that arc and produce sparks. So you have to produce a pretty large voltage. I don't know what these typically run at, but it's going to be fairly large. And then not only just arc, but you need a lot of electricity to pass through it. So your substrate, if it's conductive, it's pretty easy to do. The steel conducts electricity. You bring a tip, which is also tungsten, right? It could be a different metal, but tungsten's nice because it won't melt, right? It melts at a very high temperature. You pass a current and it starts to arc through it and you get localized melting. That arcing of all that electricity locally melts your metal. That's what you want because you want it to, as it solidifies, now be joined to the piece of metal that you squished it next to, right? Yeah, Ashton?
So the tungsten, because the hydrogen point is inert gas, because you don't want the gas to react with the metal you're using.
Yeah, if you do this without what's called a cover gas, in this case it's argon or something, without a cover gas, if you melt metal, especially something like a steel, it's going to oxidize. If you get oxidation at this junction, that junction's going to be weak and it's going to be prone to failure. But if you're blowing argon over it, then you're pushing all the oxygen out of the way so that you locally melt it and there's no oxidation, or there's less oxidation, okay? So that's TIG welding. So they're welding these different pieces together, okay? The end pieces were still sticking out, so again, they locally heat those up and bang on them, and then they weld them shut. And now you've got something that looks more or less like the hammer, okay? They're grinding away the excess from the welds, because again, welding is just melting. And so there's this pool of metal. It's tough to get it really fine, so you often do some cleanup afterwards. You clean off that extra pool of metal there. They're starting to polish a little bit, getting it pretty clean. Okay, now they're moving to the ingot that's going to be part of the pommel, I think. Yeah, the pommel. Okay? Why they use bronze, I don't know. Maybe the color, maybe the density. I'm not sure what their rationale was. But they used a hammer forge. They weren't hammering that by hand. Did you notice the machine that they put in? They heated it up and then it was just pounding on it. All that is a blacksmith of like the 21st century. Instead of having like big burly arms, which these guys do have, right? They have a machine that does the pounding for them if they're feeling a little bit tired, which is pretty rad, right? They're drilling this out, so it's going to sit at the bottom of the pommel, right? So, or the pommel sits at the bottom of the handle, excuse me. Okay, this is cool. The hammer in the movie has these sort of like Gaelic-y looking patterns on it, right? So this is going on the pommel, but they're also on the hammer itself. So this piece, they took brass or something, they cut it out by hand, right? They sort of drew it on there, traced it on, then they cut it out by hand. Now, how do you make something stick to bronze on the bottom of this hammer, right? They're doing something called brazing. What on earth is brazing? Anybody know what brazing is? In years past, we had lots of fabricators in this class, like answer these questions left and right. So brazing is basically soldering, but on a larger scale, right? You still use something kind of like a solder that you heat it up. You take the two materials. In this case, you've got the copper and the bronze, or the whatever that inlay is made out of in the bronze. You put the solder type material around it, all over it, and then you blast this thing with heat, and surface energy is going to draw that in the cracks between it. So all that extra material, that's why he's torching it. It's getting sucked into the gap between there to reduce surface area, and then it solidifies just like any other solder does, and you've basically done a large-scale solder job with this, right? So that's going to make it stick. You have to clean all that goop off afterwards, so that's them polishing it. But it's a nice way to bond metal to metal, is brazing. It's not the same as welding, because welding means that you melt one of the work pieces. This is a third piece. So you've got your piece A, piece B. You're not melting either of those. You're melting some other material that goes between them, and that's what gets solidified. Whereas welding melts one of your two work pieces, right? Okay. Now they took a look at the hammer itself, and you see the hammer, it's got that sort of funky pattern. So they took what's called vellum. Anybody knows what vellum is? Vellum is dead baby animal. Sorry, folks who don't like that. But that's what they use. I don't know why. It works well, apparently. What they can do is they can lithographically put down a pattern. Lithographically means that you use light to modify the vellum in a certain way. Like you shine light only on a certain pattern, so you mask light. The light comes down, and where it hits your sample, it's going to modify it. And it's going to allow ions to transport through that material, right? Just like the batteries have like the salt bridge that allowed ions to move, but it didn't allow electrons to move. We want something that's going to allow ions to move in certain spots where we shined the light, but not elsewhere. So if you see this, there's the green spots on this. We'll show it in a minute. That's the spots where they've modified it, where ions are going to be able to travel, okay? So you see that. They put it on there. They tape it in place. Okay? You've got the regions where ions can travel and regions where it's blocked. You now take electrochemical solution, right? This is just what? This is just ions, right? They're taking ions here in solution. They take, so the polymer resin silkscreen, that's what they use with the UV light source to put that pattern on that vellum. Here they have just it's going to be a DC, I think. Yeah, it's going to be a DC driving force. You hit the DC button as opposed to AC, because what they want to do is they want to etch one direction. They don't want to apply ions and pull them away, apply ions and pull them away. They just want to continually etch away in certain spots. So he's going to apply a DC current. He's going to have a carbon counter electrode, which is right there. That's the carbon counter electrode on that. He said glorified salt water, right, with this cotton wick. So they've got graphite on the bottom beneath that, a cotton wick, lots more electrolyte solution. They're going to pass it over that, and what you're doing is you're forcing electrical current from the anvil up to the electrolyte into your little thing that he's holding in his hand. What that's doing is that it's stealing electrons from the metal, which is making iron metal turn into iron 2+ ions, which are now not there anymore. They're just dissolved in solution. So it's etching it away, but only in certain spots. So as he does this, you can see it sort of bubbling in one of these images here. They're etching away just certain spots of it with just basic electrochemistry that you guys have already learned about, right? I don't think they have any idea of like the science what's going on here, but it's pretty basic. All they had to do was a DC current, and they had to pull electrons away, which caused it to etch out that awesome sample there. Okay? So now that they've got that, they go ahead and finish putting this whole thing together. They got a steel pipe that's going to stick in the top that they can screw this into. They made the hammer empty because I think he says at some point here, if it was fully steel, it'd weigh like 200 pounds, and nobody would be able to lift it up. So it's actually hollow. Okay, right? So they're screwing that in there. At one point he says that he puts a lead shot inside of it, and then people try and lift it up, and they can't figure out why it's so heavy. Here he's got a bunch of different metals. I can't remember if it was nickel or what, going around the pommel, though, wrapped in leather. Most of the cool material science is done, though, at this point. Okay? So we'll probably wrap up here. Well, let's jump to the end. Let's see him smash the fruit and whatnot. It feels right. Okay, so there's the hammer. They smash stuff with it. It looks pretty rad. That's material science, right? So Blacksmith, for a very long time, have been making things like swords and hammers and what have you for a very long time. But they didn't understand what's going on. It was only until like the 50s, 60s, thereabouts, that we started to understand why is it that they do these different heat treatments, different quenching, why they can weld and join materials in different ways. And so we're going to be talking about that some of that in today's class today. And a lot of it has to do with dislocations and how they move through materials, okay? So last chapter we talked about two different types of dislocations. We said that there's edge dislocations and there are screw dislocations. A screw dislocation is the one that looks like the parking garage. This thing sort of spirals through the material. Whereas an edge dislocation is an extra half row of atoms that got shoved into your material, okay? Both of these can, under the exact same stresses, produce the exact same deformation with two different mechanisms, right? So let's take this one. This extra half row of atoms. If I now shear this material, so I'm pushing the top and I'm pulling the bottom, that extra half row atoms can travel through and then pop out at the end. And in the end, I have an undeformed material. It's a deformed material, but there's no dislocation. The deformation got rid of the dislocation. This is now a defect-free material that has an extra half row of atoms sticking out the end. Okay? I can apply the exact same shear force, but this time to a material that has a screw dislocation. And the screw dislocation is going to travel that way, whereas the edge dislocation traveled that way. But in either case, as this thing screws that way, it will pop out and produce the exact same deformation. So both of these dislocations, if they're able to move, and that's the key thing here, this thing moved this way, this one moved that way. If they're able to move, then you can produce deformation, right? So on one hand, you want dislocations in your material, right? And you want them to be mobile if you want a ductile material. This explains why you heat things up if you're a blacksmith, if you want to pound on it and have it bend easier. By heating it up, you give it a ton of thermal energy, which allows these bonds to break and reform as this dislocation moves through the material. If it's at a low temperature, you don't have the thermal energy to break those bonds, right? So dislocation motion is really low, okay? Again, you can sort of see that. Here's our extra half row of atoms. Here it's traveling through the material, and then it pops out at the end, right? Dislocation motion, we have a name for that. We call it slip. The reason why is because it slips. The atoms sort of slip past each other, and they happen on specific crystallographic planes in specific crystallographic directions. It's not just like any atoms can slide past. In fact, they happen on the highest density plane in the highest linear density direction. So if we go back to, say, FCC, right? If we draw our FCC crystal here, way back in chapter 3, we talked about our highest planar density plane, and we decided that in FCC, it was this 111 plane. And that becomes a little bit easier to see when we draw our atoms, right? The atoms are located on the corners, but also on the face centers. So top, bottom, right, left, front, back. So these ones right there that I'm filling in, those ones are intersected by that plane. Those 6 atoms there that I've drawn. The plane cuts through all of those, right? Or if we were to sketch just that plane, looking straight down on it, we'd have an atom in the middle, and then these ones on the corners, right? We've really got it packed quite densely along that plane. It's the highest planar density plane in the FCC lattice. So slip is going to happen on that plane. These atoms are going to be able to slide past each other more easily because it's the highest planar density plane. Okay? So that's the slip plane. Now, which direction is it going to slip along? It depends on your loading direction. If you're loading it in a way that's sort of maybe this way, then you can imagine that it's going to slip along the direction which is along this direction. That's going to be along these triangle sides. Those are our highest linear density, right? This has a lower linear density of atoms than right here, so it's going to slip along that direction. So really when we say slip or a slip system, it's a combination of a slip plane and a slip direction. It's both of those taken together, okay? Now there is a mistake on the homework that I just caught this morning with a student. The slip system that I gave on the homework on problem 1, use it, finish the problem. You've already been working on it, so don't go back and change it. But technically, the direction has to lie in the same plane as the slip system, and I messed it up, and it isn't. I messed up the negative sign on one of them. So go ahead and calculate that problem as it is, but realize that in an actual slip system, the slip direction needs to be in the plane. So for example, if this is the plane of my materials, all of these directions, 360 degrees, are acceptable. The ones that are not acceptable are ones that go out of the plane, right? Those are not in the plane anymore, and that's what I did on the homework. So sorry about that, but you can solve it anyways. Okay? All right. Dislocation density is an important thing to realize. If you were to add up all the dislocations all the way through your material, they technically have a length, right? As they travel through your material, they travel some distance through your material. So if you could add up all those dislocations and divide it by the volume of your material, then it would be a length divided by a volume, right? So meters squared divided by meters cubed. You're going to end up with something over area, right? Over a length squared, okay? So that's typically how they characterize dislocations. Or another way to think of it is if you chopped your material right in half, and you were able to take a look at that cross-section and count up all the dislocations that you ran into, that's the dislocation density, right? Per area, how many dislocations are you chopping into, right? So what numbers can we expect? They can be as low as 1,000 and as high as like 10 billion, right? Or in extreme cases, like silicon that they use in semiconductors, right, for your phones and stuff, we already said that those are like 99 purity. They're almost 100% silicon atoms, but they're also perfectly arranged. You can have something like 1 dislocation per square millimeter, which is bonkers, right? That's 1,000 times lower than the low limit that we typically see in metals and stuff. Ceramics can be lower. Ceramics tend to be more ordered than metals because you've got the 2 different cations and anions. They order because of the electrostatic interaction there. But they are still something like, on the order of 1,000-ish. Is their dislocation density. So that's dislocation density, right? As you pound on something, as you're a blacksmith pounding on it and you're cold working it, you're introducing more and more dislocations. As you pound on that material, some dislocations are annihilating to produce deformation, and other ones are being formed because you're smashing this lattice and introducing lots of disorder. So what happens is that as you cold work your metal, cold working means you pound on it at low temperatures, you can get up to really, really high values, right? And so oftentimes they'll heat treat it again to make it ductile again. And what they're doing is they're adding thermal energy, which allows these things to move. And as they move, they find each other and they annihilate. We'll show you what that looks like when these things annihilate. But dislocations can meet up and annihilate and cure the material. And so you can go from, say, like 10 billion dislocations per millimeter squared all the way down to like 100,000, 10 to the 5 or 10 to the 6 after you do this heat treatment. So you can massively reduce the number of dislocations, okay? Okay, so why do dislocations annihilate? Why do they interact with each other? Why is it, as you pound on something and you end up with 10 billion dislocations, that it makes it harder and harder to work your metal? The reason why is because they have strain fields which interact with one another. So take a look here. We've got our, let me change color. We've got our extra half row of atoms, which I'll draw in green. Here's one right here, and here's another one. So we would say that these dislocations are both in line with each other, and they have the same sign. The same sign means that the extra half row of atoms is on the same side in both cases. So think about what this does. Now you've got the extra half row of atoms both on the top side, which means you've got compressive stress and you've got compressive stress. And then on the bottom side, you've got tensile stress and you've got tensile stress. Taken together, if you were to push those things all the way together like they've done in the other figure, where we've got 2 extra half row of atoms next to each other, it's going to generate really severe compressive stress and really severe tensile stress, right? These atoms are being pulled apart on the bottom. They're really being smashed on the top. So that is unfavorable. You've increased the overall energy of your system by forcing 2 dislocations of the same sign next to each other, right? So because of that, dislocations of the same sign repel one another. They're going to want to push away from one another so that these strain fields don't overlap. Okay? And you'll see that all the time with dislocations. You'll see that there's sort of like an average distance that they separate themselves. That once they get a certain distance away from one another, these strain fields aren't interacting as severely, right? Another thing that we can realize is that if you've got dislocations of an opposite sign, then it's the exact opposite scenario, right? If you've got something that's opposite, right, you've got this extra half row of atoms here, and this extra half row of atoms here. Well, in one case, you had compression up top, but this case, you've got compression in the bottom. And then in the other case, you've got tension in the bottom and tension in the top. So you could fix this whole problem, and these things will feel an attractive force to one another as the tension and the compression regions want to heal themselves by going towards one another. And then all of a sudden, they're going to combine, and that extra half row of atoms is just going to become a regular lattice. They're both going to annihilate, right? So you'll go from having two dislocations of opposite sign to no dislocations in that spot. Are there questions on that, on dislocation annihilation? No? Pretty straightforward, I think. So that's why dislocations of the same sign repel, opposite sign attract, and then they can be all sorts of other signs. Like, they don't have to be perfectly anti-aligned or aligned with one another. They can be sort of off by a little bit. And on average, due to them not being perfectly aligned or anti-aligned, the average interaction is repulsive, right? So if you have more and more and more dislocations, the average interaction is that they start to repel one another. That means it's harder to move any single dislocation through your material. It's just like people in a subway, right? If you're trying to catch like rush hour train in the subway, and the subway is chock full of people, on average, it's harder for you to move through that area and get to your train than if it was totally empty, right? Yeah, question, Hector?
Would they ever interact with each other as far as the compression versus the tensile? Because what I'm thinking is, if the tensile is pulling out and the compression is pulling in, would the compression have the half row strings go down to the tensile and pull out?
In a single dislocation? So, two questions I'm not quite sure you're asking. First off, if there's two dislocations of opposite sign, will these two fields interact with each other? Yeah, you betcha. They will come together. These atoms are crowded. These ones are being pulled apart, so they're going to come together and heal. So that will annihilate. But the other question that you might be asking, I'm not totally sure.
Like that single one you have in B.
Okay, this one right here.
They're compressing and the other one's pulling.
Yeah, but how could you fix... I see what you're saying. Like,
compressions go downward where
yeah.
least strain, least...
Yeah, you're asking the question like, can this region interact with this region? Right? This is like under tension. This is under compression. Can these interact in some way?
The way the picture's shown is that going linear, but that doesn't really happen in real life, right? It just goes wherever it needs to go to. Least.
It's going to want to minimize its strain energy. Yeah. But the problem is there's no way to arrange this single dislocation in a way that makes it any better. If you try and draw these atoms with an extra half row in there somewhere, there's no way to make it any better. So it's sort of like a fixed quantity that this has, okay, for a given lattice. Now, different lattices have different bonds and different sizes, so the overall energy will be different. But for a material, every dislocation kind of has a fixed energy associated with it, okay? Are there other questions I can answer about dislocations, how they interact with one another, how they go away when you heat them up? Okay. Okay, let's keep going. So you can actually see this, which is pretty rad, right? If we go to YouTube, we go back to the 50s when they loved to make these bubble rafts, you can see that here's a dislocation over here with an extra half row of atoms. Here's one with an extra half row of atoms. They're going to nudge it from the outside, and these two sort of came together, and it created a third, right? Let's look at a different one. How about, so that was two dislocations creating a third. Let's look at different dislocations interacting with one another. Okay? Here you've got the following scenario. You've got three dislocations that are lined up with one another vertically. Why do they line up vertically? Turn to your neighbor and discuss why do you think they might line up. They're all the extra half rows of atoms is one direction, but they line up vertically. Why do you think that happens? What do you think? What's going on here?
I'm not 100% sure, but I'd imagine something along the lines of whatever strain or pressure or whatever is causing the defects is happening in a vector component that's causing the same in all areas.
So think each one of these as they're stacked up on, say, the top side, that's under compression. But this one on the bottom side, it's under tension. So like that compression and this tension, they overlap. And it overall makes it better, right? Because overall, like the strain of those two separate is high, but since they're opposite sign, it heals the lattice a little bit for them to line up vertically. Even though they're the same sign. Okay, what do we think? What's going on here? Why do they line up? Anybody have a good thought? How about in the way, way back in the blue flannel? What do you think's going on here? Why do they line up? No idea. Phone a friend. Who can help you out? Because science. Let's go back to our drawing, right? You've got a bunch of dislocations. They've all got a strain field associated with them, okay? On the top, it's compression. On the bottom, it's tension, if it's this one, right? Imagine if they're the same sign. If I draw another one of these things, below it, stacked up vertically, then it's going to have tension and compression in the same regions, right? There's our compression. Down below it would be tension. What happens is that this compressed region is interacting with this tensile region. And it overall kind of heals it. It lowers the energy for those two things to overlap with one another. Therefore, you'll often see dislocations stacking up like this because it just reduces the overall lattice strain, right? So that's what we're seeing in this bubble wrap video. Like this is a real example of this, where you can see a dislocation stack up. Meanwhile, you've got these two, which are the same sign, basically on the same plane as one another, and they're repelling one another. So let's watch what happens here. So they're going to mess with it. They're going to push on this with sort of like a straw a little bit. They're going to move this dislocation a little bit up there. He's talking about the interaction between those two right now. Now he's going to move it and watch what happens. Okay, he's going to mess with it. He's going to drag it down, and it lines right up. The reason it lines up, first off, the reason that it went to the right, because it didn't feel that repulsive force anymore, because now that thing was brought below it. And moreover, it feels now an attraction because the tensile region below it lined up with the compression region, and so they line up. This is pretty rad, right? The fact that we can see this in bubble rafts is helpful, but this is also happening at the atomic scale. This is a pretty good model to simulate how atoms interact. Okay? Then the last one is take a look at this. In this case, now they're going to have an impurity atom. Okay? So the impurity atom is slightly smaller. So they blew a bubble that's either bigger or smaller. It looks like it's a little bit bigger. The one that they're pointing at here. It's maybe a little bit bigger. So the region around it is now under compression because you've got this slightly bigger bubble there. So if we go ahead and hit play, what will a dislocation do? Let me ask you this. What should it do? Maybe turn to a neighbor. What should the dislocation do? Should it ignore it? Should it care about it? What should it do with respect to that bubble, the bigger bubble? Talk to your neighbor. Okay, what do we think? Any thoughts? What's going on here? Let me do the red beanie and the black in the way back there. What do you think's going on? So the question is, if a dislocation comes by this impurity, which is sort of locally compressing the atoms around it, is it going to care about it? Will it interact with it? And what will be the nature of its interaction? What do we think? Because these dislocations can move. You saw that you can slide them around as you apply stress to this material. If it goes zooming by that spot, what might happen? Any thoughts?
I would assume it's going to interact, but I'm not quite sure.
Let me ask you this. If it has a compressive region, do you think it will interact with the tensile region of your dislocation? Attractively, right? It's probably going to be attracted to it. So let's see what happens. Okay, so dislocation comes by. It's going to come by again, and it's stuck. Now it's stuck on the other side, but of the opposite sign. Do you see that? You've got two dislocations of opposite sign coordinating that defect, right? So you've got the two tensile regions of two dislocations clumping up near that compressed region because overall it reduces that strain. Okay? So because of this, let me ask this question. Now turn to your neighbor. What if I make an impurity in an alloy, take sterling silver. Sterling silver is not pure silver. It's silver with something like 8% copper atoms in it. Why does it make the material harder and stronger? What does it have to do with dislocation motion? What do you guys think? What do you think, dude? Why does impurity atoms, like copper and sterling silver, make it a harder, stronger material? It has exactly to do with this.
I would think it would cause the compressive and tensile regions to line up and make it a tighter bond or something.
You're thinking along the right track. What's bonded? What's bonded? You're really close. All right, what do you guys think? How does this make it harder, stronger, more scratch resistant?
If you have the imperfection in there,
Okay.
and it creates a compression, a compressive force around it,
Okay.
if it's bigger, then the dislocations, like being attracted to it and doing what it's doing right there, how the compression is attracted to the tension, that would like counteract it, and it would make it, I would think it would make it stronger, because then it doesn't have that being at the
Oh, you're real close. Yeah, you're real close. Think about how do materials deform? What do dislocations have to do? We started the class with it, right? We showed you an edge or a screw dislocation. They both have to move to produce that deformation. Do you think this is easier or harder to move? Yeah. Okay. Remind me your name real quick. Sam's going to explain what we think's going on here. Why is it that when you take silver, you dope it with copper, that it's now a harder, stronger alloy that people like for jewelry because then it won't scratch?
So when you have the embedded atom, whatever it is, your replacement one, if it's copper instead of silver, then having the dislocations focus on it or be attracted to it, then makes it harder for it to move or for the planes to move.
Yeah, the dislocation can't move anymore. We started this class showing how deformation occurred, right? If we go back to it, deformation happened like this. Go way back up here. We said in order to get this thing to pop out at the end, right, which is a scratch or a dent or a breaking or whatever, right, this dislocation either had to move that way because it was a screw, or the edge had to move that way. But in either case, the dislocation had to be mobile. It had to move to create that deformation. And if you have this scenario where those dislocations are what we call pinned, they're pinned in place, pinned dislocations are dislocations with reduced mobility, you have a harder, stronger material. In fact, that is one of the key things I hope you'll take away from this class. If you want to make a material harder or stronger, make it harder for the dislocations to move. Right? That's a key takeaway from this class. If you want to make a material softer or more ductile, give the dislocations an easier way to move, and you've made it softer or more ductile. Okay? Now, there is the possibility that impurities can move in a material. Next chapter will be all about that. It's called diffusion. But that is way slower than these things move. These things move at like speed of sound, like really, really fast through your material. Atoms hop through your lattice really slowly. Okay? So if that's a copper atom in a silver lattice, it's basically stuck there. It's not moving, so your dislocations are stuck there with it. Okay? Okay. So dislocations can do some interesting things at surfaces, like grain boundaries. They can annihilate there. They can form there. Because of the irregularities along these surfaces. Okay. But we've already talked a little bit about slip systems, what they are. The next question is, let's do a sample calculation. In FCC, remember FCC was up here. We drew this red triangle, right? And we said that is a slip plane because it's the highest density plane. And we said along that plane, there are directions which are highest linear density, right? So we could start counting these things up. We could say, okay, in that plane, there's 1, 2, 3 directions, and we're going to count forward and backwards as the same direction, right? So there are 3 slip systems in that triangle. The question is, in the overall crystal structure, how many slip systems are there for FCC, right? So I think this is our next clicker question, I think. Oh, no, it isn't. Okay, so it's not a clicker question, just a group question. I forgot to program it. How many slip systems should there be in FCC? So turn to a neighbor, let's count them up. How many should there be? Don't double count, okay? So how many of those triangles can you draw that are crystallographically equivalent, and then add up these sides? Okay, what are we thinking? How many slip systems do we count? I'll say it's a little bit tricky. If you start just drawing these triangles and counting the sides on them, you start double counting really quickly. So there's kind of a trick answer here. If we look at our crystal structure, the directions are along the faces, right? You've got one here. That's one slip direction. But you could draw a different triangle that has it going that way. So there's 2 per face, and there's 6 faces. So you've got 12 as your slip systems here, right? So in the FCC system, there are 12 slip systems on which you can slip. That's actually a really high number. It means that no matter which direction I'm applying a load on this thing, whichever direction I'm coming at it from, there's some way where the atoms can slide pretty easily to accommodate that, to get slip. Because of that, FCC metals are very ductile metals. Copper, gold, these things are FCC. They're easy to deform because they have so many slip systems. But not all metals are FCC, and other ones don't have as many slip systems. Take like, FCC and BCC metals, or HCP is even worse, right? FCBC are good. I meant to say HCP is even worse. It only has 3 or 6. HCP, if you look at it, looking down on the hexagonal lattice, you've got only 3 or 6, right? And so it's way less ductile. These things tend to be much more brittle, okay? And we're actually going to see an example of that probably later this class. Maybe next class. Okay? All right, let's talk about slip in single crystals. Now that we've identified what is a slip system, it's a plane and a direction. Let's talk about how to calculate this for a single crystal. Last chapter we said that if I apply a force to this, normal to its face, I think that I'm only applying a normal force, and therefore there should be no shear. Atoms slide past each other due to shear. So you'd say there should be no slip here because there's no shear. But then we remember, oh yeah, I forgot. If there's some plane, even if it's an imaginary one in this material, now the force is like that, and there is a shear component. There's some direction where there is shear. So we can actually figure out what this plane is. It's going to be our slip plane. What the direction is in that plane, our slip direction. And we can calculate the force which will cause slipping to occur in that direction. The formula looks like this, right? You've got your resolved shear stress, meaning even though you don't think you have a shear stress, on some plane there is a resolved shear stress. That's equal to the stress that you apply multiplied by the cosine of 2 angles. The angles are these two. One is between your applied force and the normal to your slip plane, and the other one is between your applied force and your slip direction. These 2 angles you need to figure out in order to solve these problems. Actually, you don't need to know the angles. All you need to know is the cosine of those angles, because that's what this formula asks for. Right? It wants to know the cosine of those 2 angles, and then you can solve for the resolved shear stress. Okay? So how do you figure out those? It's tricky. You have to go way back to whenever you learned about vector geometry, right? But if you've got 2 vectors and you need to figure out the angle between them, let's say vector A and vector B, the angle between it, which we'll call theta, we know that the cosine of theta is equal to what? The dot product, A dot B, over what? The magnitude, or the length of these 2 vectors multiplied by each other. Okay? So, if we're going to do an example of this in a second, if these are all vectors, something like this is like the 0, 1, 0 direction, and maybe this is the 1, 1, 1 direction, and this is some direction in the plane, right? You could figure out the matrix geometry to figure out the cosine of that angle pretty easily. Okay? If you don't remember how to do that, we've got awesome videos that walk you through how to do dot products and cross products. Oh, not cross products, just dot products and lengths. That'll show it pretty easily. Okay? Let's do an example real quick. I think that'll be the easiest, right? So we already talked about how to calculate this. We use the dot product rule. Let's get down here. Okay. So we're going to calculate the tensile stress that is applied along the 110 axis of silver to cause slip on the 110 plane in the 011 direction. The only catch here is, how do you know, right? This is your applied force. This is maybe like the slip direction. And then you've got like your plane, and you've got this normal. This one here is the direction normal to your plane. Or in other words, it's like if there was a flag post sticking out of that putting green, it sticks straight up from it. If the whole plane is the 111 plane, what will be this direction right there? What will be the normal to it? In the cubic crystal system, it's easy. It's just the 111 direction. And we can see that. In a cubic system, it's really easy to see. So I'm showing you now the cubic crystal system, and I'm showing you the 111 plane. And if I plot a 111 vector, you can see that that's normal to it. Those are 90-degree angles. Okay? So that's perfectly normal to it. That only works in the cubic crystal system. If you're doing anything else that's not cubic, you have to do a kind of gross matrix transformation. So here's an orthorhombic crystal. If we look straight down on it, these sides are not the same. Like that's 5, that's 10, that's 15, or whatever it is, right? They're different sides. And so if we look at the 111 plane, it's the same, the 111 plane, but that vector, the 111 vector, is now no longer normal to it. You see that? How it's not a 90-degree angle with it anymore? The real one would be 90 degree like that. So you have to do a transformation, and we're not going to do that in this class. Just realize that in this class, when I asked you to figure out the normal to the plane, I'm only going to ask you to do that for a cubic system, because then the normal to the plane is just the same number as the plane. If it's the 111 plane, then the normal to it is just the 111. If it's the 001, then it's the 001. Okay? It's just the same as it. So we've got 3 minutes left, so let's start working on this. We'll start it together. It says that the critical resolved shear stress is 6 megapascals, meaning in your material, the resolved region where if you go above 6 megapascals of shear stress, it will start to slip. So it wants to know, what overall stress can I apply to it in a normal direction, right? What can this stress be in order to achieve this as 6 megapascals, in which point it will start to slip? Okay? So the way to do this is we just figure out what our different vectors are, right? This one we decided is our 111 vector. This one, it says that the stress is being applied along the 110 direction. So this up here is 110. And then the slip direction, where it slides, is the 011 direction. So if this is phi, and that is lambda, then we know that the cosine of phi is equal to 111.110 divided by the length of 111 multiplied by the length of 110. So let's go ahead and do that. That's going to be, I'm going to give myself a little more room. Come down just a little bit. Right? So cosine of theta is going to be equal to 1 times, how do you do a dot product? You take x times x plus y times y plus z times z. So that's going to be 1 times 1 plus 1 times 1 plus 1 times 0. Right? So that's 2 in the numerator. Okay? Now the denominator, we're going to take the length of the vector. How do you do the length of a vector? Square root of each term squared added up. Okay? So the 111 would be the square root of 1 squared plus 1 squared plus 1 squared. Then that's going to be multiplied by the length of this vector, which is just square root of 1 squared plus 1 squared. So on the top we had 2, and on the bottom we've got square root of 3 times the square root of 2, the square root of 6. Okay? Any questions? Remember how to do that? If not, watch the YouTube video, come do some examples. We can do the same thing with cosine of lambda. And we will pick up there next time for our next clicker question.